All right, let's get going. Hello, everyone, and welcome to today's webinar. My name is Alan Huang. I am a senior product manager for data center at IP Infusion. I will be your host today. I'm joined by my co-host, Sujay Gupta, who is a senior solutions manager at Edgecore. Thank you, Sujay.
Hi.
So we are thrilled to have you join us. Today, we will be exploring the exciting topic of open Ethernet networking for modern AI ML workloads, a blueprint for building the AI factory. Before we dive in, a couple of housekeeping notes. All attendees are muted during the presentation. You can submit your questions at any time via the Q&A tab or section in your meeting control panel, and we'll address them during the Q&A session at the end. And so here is the agenda for the webinar. After brief company introductions, we will first look at AI solution ecosystem. Following that, we'll provide you with practical network design and config examples learned from active projects based on our AI networking solution. We will then look back at the history of Ethernet versus InfiniBand and look forward at future development, including Ultra Ethernet transport support. So without further ado, let's get started. So for those not familiar with IP Infusion, we've been in the networking software business for 25 years. We began by providing protocol modules in source code format, and for more than a decade now, have delivered a full-featured commercial networking OS in binary form, running on white box switching and routing hardware such as the Edgecore ones. Widely adopted open source projects you may have heard, such as FRR, Quagga, and Bird, all trace their roots back to our Zebra routing protocol software created by our founders. So today, we're proudly serving more than 600 customers worldwide. Now, open networking can mean different things to different people. At IP Infusion, it means we're giving customers the freedom to choose the switching, routing platforms, and optics as well that best fit their needs, while we're still delivering the simplicity of a complete system in terms of buying and the support. Our solution combines our open choice with the assurance of comprehensive level 1, 2, 3, 24/7 professional support, not just for our software, but for the entire system. Now, these are our top customers, the service provider and the data center operators on the left, and networking equipment manufacturers on the right. This roster highlights the broad market presence of IP Infusion's networking software solutions. So I'll hand over to Sujay.
Thank you, Alan. So about Edgecore, so Edgecore is not a new company. We've been there for about now 15 years. But when we root back to our parent company, which is we will cover in the next slide, we are about 35 years old. So we have been, so Edgecore is basically a go-to brand market for our parent company, Accton. And we have been primarily making equipments for networking across the entire spectrum. So next slide, Alan. So about Accton, parent company. So the Accton is a well-known company, well-known figure in the networking OEM business, and the top tier one OEM companies have at some point of time sourced their hardware from Accton. So we are spread across the world, and we have a large employee force as well as different factories at various locations with support centers. And the key mission and vision in terms of what Accton comes out with is always it comes out with innovative products, which is latest in technology, and which can be adopted and used by different segments of the network. Go to the next slide. So in terms of the product portfolio, as you can see, we cover quite a large group. So on the left side, you see we have the AI cloud data center solutions. And this is an area we were going to cover more in details in this presentation. But then that's not just the only product line. On the service provider side, we have a SKU of products which range from pre-aggregation to aggregation and core. And then on the access side or the enterprise side, if you see on the right-hand side, we have actually a large portfolio of products, right? So we have right from Wi-Fi access points to PoE switches to Ethernet switches to cell-side router gateways, right? So we are not going to delve into all of those, but we have this complete portfolio. And one important message is along with OcNOS, we have a combination of hardware and software in all these three segments. So while our focus on this on the data center side, we have expertise for a service provider of tier 1, tier 2, tier 3, or even enterprises with hardware and software combinations, including support. Next slide, Alan. So since we are in this particular webinar, we're going to talk more about the data center portfolio. I would like, this is a quick kind of view of what are the different products we have. But I'd like you to look into the top two red blocks over there, right? So this kind of tells you where we are in terms of in terms of a customer retention and a customer base. So in 2022, we are actually Edgecore switches have been used in more than 50% of the data center by the top, largest marketplace in the world. And that system has been running very well in the last 3 years. And if you come down to this year, then we have actually used 400 gig switches in the largest payment gateway, using Edgecore designs. So, this is sort of a quick, view to tell you that how stable and how robust the products are in terms of our hardware. But then if you come down into the different kind of products we have, so this is a lot of products over here, right? So, but we wanted to give you a little bit of a summary as to what is what. So the ones which we have marked in green in color are essentially, if you see on the bottom left-hand side, those are essentially designed for AI data centers. So the essence of these particular switches are, they have high radix. So when I say high radix, then essentially they have the capacity to spray packets to multiple GPU systems, multiple GPU clusters, under fine-grained control. And each of these are designed for a very good east-west traffic load, which we will again understand a little bit more in the following slides, right? So given that, you can actually use these switches, the ones which are green in color, in a combination of a leaf or a spine switch in the AI data center. If you come down on the blue ones, the blue boxes, so those are basically the switches which we have designed for regular enterprise and cloud data centers. And how they essentially differentiate from the ones which are green in color is you have the port speeds which are much lesser now. So they have 25 gig, 100 gig, 400 gig. And in general, there's an oversubscription ratio. What that means is essentially the number of servers it's connecting to and the number of uplinks. There is a 1:2 or 1:3 kind of oversubscription ratio. And that suits the kind of traffic because, for enterprise, you don't expect a complete bisectional bandwidth traffic to be flowing. And generally, the traffic is both north to south as well as east to west, unlike in an AI data center, right? So maybe you're taking a design with a VMware solution, right? So in those cases, the enterprise cloud DC solution is a good fit. On the bottom south, the switches which are not marked with any square blocks, those are essentially used for management. And overall, we have a complete portfolio along with OcNOS. So the ones which we have marked in orange in color are the switches which runs perfectly well with OcNOS as a combined solution. Right. So with this, let's go to the next slide. So again, what we have done in this slide is taken up the same portfolio, but given a little bit of a deep dive that when I want to use these particular switches in an AI data center, then what are my design choices? So as we just talked about, the switches which have high radix capacity are generally not designed for oversubscription, are the ones which are high in terms of throughput. They have low latency, and they essentially become the blue part, the one shown in the AI fabric switch, right? Which is about 51.2 terabits, and going forward, it's going to increase more. But when you come to the storage fabric, right, because all data centers, you have a server and then you have a storage part. So when you connect these to the storage switches, then the storage switches should have some kind of a unique feature, right? So, and that's what we have mentioned in the red color here. So one important thing you may notice is these are all running a chipset which belongs to a Trident 3 family, a Trident family. So how are these fundamentally different? Fundamental differences, these have higher buffers. And why this is required is because when you're pumping traffic in and out of the storage networks, you need to make sure you don't have these buffer segment losses, right? It has better QoS because you want to prioritize certain packets over certain packets which should not be prioritized. And they're also rich in terms of features, right? Which is not really required when you come to the AI data center switches, which is essentially east-west traffic. All you need to do is connect the GPUs. So this was a little bit of a breakdown as to what kind of a chipset we're using and why when we come to AI data center breakdown. We can take any questions after this call. Next slide, please. So in terms of an Edgecore AI solution, so we just talked about the switches, but as a company, Edgecore doesn't just have the switches, right? So which is mentioned on the left side here. We also have GPU servers, right? So we have the other than NVIDIA, so the other primary competitors in the market, it's basically the AMDs and the Intels. So we have designs from them, and so we have 3 designs which you can see on the left hand side. And essentially, the question everybody may have is that how does it compare to NVIDIA, which is the market leader, right? So these essentially are in around the NVIDIA H100 class of servers, right? And going forth, we'll be adding more designs, which will be close to the B200. So given the server, the data center switch combination, and on the bottom right-hand side, you may see we also have transceivers. And these transceivers generally take a large part of the entire cost of the BOM. So including all of this, we are, along with the software piece from OcNOS, we are in a capacity to make a complete rack, right, for AI data center. And that's the key message over here. Both the hardware as well as the software pieces available. Next slide, please. So now we basically talk about, what's the new thing which is coming up. So we all know AI GPUs are the new thing coming up, right? But the message here is that when a company is migrating or taking practices, their services or their operations with AI-enabled processes, then if you see in the AI lifecycle, the typical journey is you start everything from the cloud. So you have multiple cloud providers, as you can see on the left-hand side. You start your experiments over there, right? And then eventually once you have your models kind of trained, you've understood what you want to do, you want to migrate them back to your own offices because you want to optimize it better, right? And because we all know the concepts of hallucination from AI data models, it gives you totally wrong results. You want to make sure you fine-tuned it for your purposes. So that kind of a background work is required when we go to office. But then there's an important phase which comes in, which is called as two data center, right? So why this is very important? Because what happens is if you start running everything from the cloud, and your entire capex, your entire opex keeps increasing over a few cycles. So on the top, if you see, there's a small block which tells an estimation that if you run GPU as a service on the cloud and versus on-prem, then you may get about 74% savings when you actually migrate the entire load, entire design back to your own local data centers. So that is an important phase, uh, making a data center of your own. And we have seen this already happening with some cloud service providers. We're working together with IP Infusion, colo providers, as well as enterprises in the range of who work in logistics, oil exploration, and different core sectors. So they are actually building data centers of their own and running, AI solutions over there. So AI lifecycle is not a single thread journey, because once you essentially design and develop a training model, you use it, you have to keep updating it. So investment in a data center is very important from an enterprise perspective. That's the key message in this slide. Go to the next slide, please. So when you eventually have a data center back home in your own enterprises, right? Then obviously you have to look into what can I do to improve the performance, so I think I can get the maximum ROI. So if you look into a typical AI stack, then the bottom one shows you the component which is hardware, which is the one which is green in color. And above that is the complete software layers. So you have a system software, you have acceleration libraries, platform, and application, right? So in terms of where we can have a control, it's definitely on the hardware piece, right? And when we talk about the hardware piece, there's definitely the GPU, then there is the DPUs. And to use the DPUs, you need some kind of a system software, like what's mentioned over there is DOCA, which comes from NVIDIA. Similarly, you might have a GPU to GPU communication, which comes from a software suite called as Magnum IO. And then, so the net message is there are a lot of software suites and software system software, which is required for you to optimize and do your required job properly. And a job could be, depending upon your need, can be gaming, can be machine learning, can be ray tracing, can be large, very LLM training models. Right? Depending upon the job, you can use the right kind of a software. But it finally boils down to hardware, right? Finally boils down to the hardware piece, which how effectively it is able to do. And there, the new challenge is coming up, because as more and more, AI models are increasing in terms of their complexity as well as the data bandwidth, you are not able to run everything on a single GPU, right? Which basically got us to the new era, which is a multi-GPU system, which we will cover in the next slide, please. So when you talk about multi-GPUs, right, there are essentially two ways you can totally design it. What you can do is you can take a server in which you can add more than one GPU, and that's what we call a scale up. So you can add multiple GPUs, and that's true because most systems now have at least 8 GPUs, including the ones we talked about, the AMDs, Intels, and the NVIDIAs. But that alone doesn't solve, many of the AI required resource problems. So the solution for that is then you have to have a multiple GPU server requirement, which is what we call as the scale out. Now, to make the scale out or the scale up essentially very successful in terms of performance, the golden rule is mentioned on the right-hand side, right? Is the data must always be available for the GPU, because these GPUs are essentially working in a parallel threading and parallel tasking mode. So if you want to use all the parallel tasks, if you want to make sure that the entire computation is well utilized, you must make sure that the data is present for it to consume at every time. And around that, there are multiple technologies which have come up, right? So like the NVIDIAs of the world have something called as NVLink plus NVSwitch. AMD has Infinity Fabric. There's a new technology coming up called as UA-Link, right? So this is between GPU to GPU. But then the challenge comes that when you want to connect a server to server, then how do you do it? Then you go back to the old world of using networking. So, and then what kind of a net topology you use, what technologies you use so that the GPU to GPU communication across servers is very good and efficient is something we will cover in the next slide. Yeah.
All right, thank you, Sujay, for setting the stage for this part of the presentation. So now we're shifting the focus to the IP Infusion and Edgecore joint solution. So IP Infusion OcNOS as an open networking OS powers a wide range of Edgecore disaggregated data center switching platforms for building out a dual fabric AI ML network shown on this slide. In the solution we have been working with the customers on, there is a AI fabric dedicated to interconnecting GPUs that is primarily Tomahawk 5 based, while the front-end network plus storage fabric as a single network handles CPU to storage networking and also connectivity and the traffic to external network. There's also a management switch in the portfolio for out-of-band device management. So the key features of both fabrics include dynamic load balancing, and that is supported on all the AI and the fabric switches. Dynamic load balancing and can avoid collision of long-lasting elephant flows. Lossless, a lot of traffic. In fact, most of the traffic, not just the GPU to GPU traffic, but also the CPU to storage traffic increasingly. All of them are becoming lossless RoCE v2 traffic, and so lossless RoCE v2 transport via PFC, which stands for priority flow control, and the ECN, which stands for explicit congestion notification, and that's one of the key features. And inevitably, there are many different types of traffic going on across the network. So there is a need for efficient support for mixed traffic types, and that's where ETS comes in. ETS stands for enhanced traffic selection. So one of the popular approaches to scaling AI fabric, which was shown in the previous slide, just in a very simple diagram, but let's take a deep dive into what that AI fabric looks like. And what is shown here is a pure rail architecture, which is a very popular one. So the slide shows this example based on the design for some of the active projects that we're working on. So it offers two key benefits. The first, if you have noticed, there's no super spine layer. That is purposely BSO. So the whole rail architecture consists of disjoint, independent closed networks with no super spine interconnect. And that way, you can minimize the number of switches required. Second, because now each clause only needs to advertise the IPs of its directly connected GPUs. The BGP routing scale is greatly reduced, just a fraction of what would be required if you were to interconnect the whole thing into a single interconnected fabric. So in this particular example, and it's mostly the case, it's the 1/8, because typically a server has 8 GPUs and you can equally divide it into 8 rails in this rail architecture. And there's, of course, the need for inner rail GPU communication. You cannot, each slice indicated by color here of a GPU fabric cannot be totally disjointed and never communicate with each other. But that communication is handled through the in-server GPU interconnect, the so-called scale-up concept that Sujay alluded to earlier, which is a fundamental capability of modern scale-up GPU server. So how is AI job executed on such a fabric? So in this example, the AI training model is partitioned across rails for pipeline parallelism. The training data set, which is indicated in the slide, It's divided first into many batches. And then each batch is further divided into micro batches. The purpose of dividing the data set this way is to enable efficient pipelining. So let me give you walk you through a workflow briefly. So for a new micro batch of data, it will be first fed into rail 1 GPUs indicated in red color. And so the red color GPUs process the first layers of the AI model. And once that's done, it will forward that rail will forward the output of that micro batch to rail 2 GPUs indicated in orange color. Rail 2 GPUs immediately begin processing the next layers. While the layer 1 is not sitting there doing nothing, and it actually immediately starts on the following micro batch. So this overlapping workflow keeps all GPUs fully utilized and significantly accelerates training. Now, as mentioned in the previous slide, the GPU scale for each leaf and the spine switches is significantly reduced thanks to a rail separation. The table in this slide lists the resultant scale for a network that supports 32K GPUs, which is a relatively high number. This is a relatively low scale for switches like Tomahawk 5 to handle. For a stable routing environment with a few updates, other than just like periodic keep alive, 130K paths or 129.056 in particular, or to be exact. The 130K paths will have a minimum impact on the CPU. Even during periods of instability or large-scale updates, such as link failures and the BGP control plane restarts, don't worry, the OcNOS has a slew of features such as a BGP peer group, a BGP, a graceful restart, BFD, and hardware-based fast link failover, and those can come to keep it under control. Now, we walked through an example of workflow of an AI job a couple slides ago. So AI job being pipelined in load balance across GPUs through the network. But that workload actually involves different traffic types shown on this slide. So I'll go from the top to the bottom. So first, as illustrated, this slide, these are the primary traffic types involved in a training job. I'm using training job example, not inference job. So from the top to the bottom, so first there is the control messaging. The control messaging is from job orchestrator like Kubeflow and distributed training layer like PyTorch distributed their jobs. The purpose of those control messaging is for job coordination and in-job scheduling, as I previously shown. The training data set needs to be read from storage, one batch at a time, and the training model state needs to be written to the storage during checkpointing, and those are the 2 and the 3 traffic types on the slide. These together with the 4th type, logs and telemetry data. So these are better handled by the storage fabric, front-end network and the storage fabric as a single network. The activation data, the 5th and the 6th, the activation data during forward pass and the gradient synchronization, reduction, exchange between GPUs during backward pass, those are highly at high throughput and highly latency sensitive, and therefore they are transported by the dedicated AI fabric. So this the table illustrates the purpose and necessity of having a dual fabric AI data center network that with a different fabric dedicated and suited for different traffic types. Now, given the different characteristics of each traffic type. The QoS requirement is different for each type, and each needs a different QoS setting. So this slide shows an example and how to do the setting by traffic type. For AI fabric, it is mainly only dealing with the RoCE v2 traffic of learning operation. So there are only just two lossless queues, one for the data itself and the other one for congestion notification packets. And however, there may be multiple jobs with a different priority and may need separate lossless queues with different bandwidth allocation, and that can be done as well. As for the front-end network and the storage fabric, similarly, there are two lossless queues, one for data and one for congestion notification packets for storage I/O traffic. Control messaging, although not requiring a lossless treatment, is very critical because it is like the brain of the whole system, and therefore it's given a high priority right after the lossless storage traffic. And logs and telemetry data is being served as best effort traffic in this example. DCBX is a protocol used to negotiate and enforce a PFC plus ETS settings at every layer 2 link, enabling hop by hop lossless transport of RoCE v2 in a routed network. So this slide shows the best practice of DCBX configuration across the entire path. So you have noticed that these switches are put in non-wheeling mode, meaning that they are enforcing their local config on neighboring nodes such as spine switches and server NICs that are in wheeling mode to accept the config sent to them. So this way, every switch and the NIC along the path can reserve consistent bandwidth, activate lossless queues, and maps class of service values to queues the same way. A key feature is dynamic load balancing. The purpose of dynamic load balancing is to optimize network link utilization, which is critical for maximizing GPU efficiency. So dynamic load balancing improves link usage by intelligently distributing traffic in real time based on link quality. Unlike the regular ECMP, which is based on a static packet header hashing, DOB uses a dynamic index, which takes into account in real time factors like link utilization, queue depth, congestion, and ECMP member availability, because sometimes the node or link may fail and it will change the ECMP group membership makeup. And that needs to be considered as well for dynamic load balancing to select the output link for a given destination prefix. So to preserve packet order, flows are not just being switched over in the middle of a flow, but rather the flows are only rebalanced after they become inactive for a predefined period. For really very long lived flows where you never get a chance to shift the flow in the middle of a flow, practically, don't worry, there's a mode called reactive path rebalancing. So even for those type of flows, if the quality gap relative to a better link exceeds the threshold, the flow may be probabilistically shifted. In real-time understanding of the network performance and the state, or simply called network observability, to AI network operation is critical. It's like the car dashboard to a driver like you and I. So the essential sensor paths are listed in this slide by leaf and the spine switches. So these sensor paths and the information carried by them give you or network operator a real-time view into the link utilization, congestion, per traffic class bandwidth usage, latency, critical optical link health, and the BGP session state. And telemetry is also key in kind of gluing everything together. So real-time telemetry enables distributed training layer to optimize GPU utilization through fine-grained in-job scheduling adjustments. For example, on the right, there's a very simple real architecture-based AI network. In this AI fabric illustration, the training layer can respond to telemetry, which is showing heavy congestion on rail 1 by offloading some of the processing, such as gradient aggregation to CPUs on rail 2 temporarily. Normally, rail 1 will carry that computation, but in the event of congestion like this, which is informed by the telemetry, it can do a different arrangement, like what I said, offloading the gradient aggregation to rail 2 GPUs temporarily. And simultaneously, with rail 4, underutilized at 10% only. So once that information is being conveyed to the AI system, it can take advantage of that and begin to start the next micro batch from rail 4 instead of defaulting to rail 1, which is already super busy with the high congestion in the network. And in this, and at the cluster level, the AI job orchestrator also plays a key role in this whole integration, and which is that it can leverage the network load distribution insights from telemetry to drive OcNOS, Edgecore, AI fabric, switch configuration changes. So these changes include things like reserving lossless queues, programming and reprogramming priority to traffic class mappings, and allocating bandwidth on a per job basis, as well as enabling dynamic load balancing on job-specific links. Dynamic job balancing may sound wonderful, but it consumes ASIC resources. So, it may be necessary that the dynamic load balancing is applied selectively, not all the time. And so with the information and the intelligence, then you can apply dynamic load balancing only on job-specific links. Back to you, Sujay.
Hey, thank you, Alan. So, so in this slide and the following slides, we're essentially going to cover two key things. So one is a little introduction about what is called as RoCE, right, and versus InfiniBand. And the second point we will cover in general is what the new technologies which is coming up, and then we will sort of wrap up this entire webinar, right? So in terms of what is RoCE, right? So if you look on the right-hand side, there's something called as InfiniBand, which is very popular and well-known. And then there's Ethernet, right? So InfiniBand was always designed for low latency point-to-point communication from a server to storage, and it was efficient. It did that job well. Ethernet was always designed for multi-purpose jobs. So when it came to the AI use cases, the AI fabrics, then we had two essential classes of use cases. So one we calling as the AI factory. In these designs, you had a training model which was sufficiently large, and you didn't have many users on this, right? So on the other hand, you had AI cloud, for example, for the likes which is hosted by Amazon or Azure, right? So in those cases, you generally have smaller jobs, you have multiple users coming in. So the choice of background technology in terms of transport was Ethernet, but for very specific high-end HPC AI use cases was InfiniBand. That was some time before. What has come over the last few years is something called as RoCE, which is RDMA over converged Ethernet. So what it does is basically it takes the benefits, which the key features, the benefits from InfiniBand, and uses Ethernet on top of Ethernet as a medium to provide a similar functionality. Right? Now, why it is so successful? If we go to the next slide, Alan. So why it is so successful is this is the left-hand side picture which you see. So what has happened is while on the extreme left-hand side, you see there's the InfiniBand stack, which was very prominent, used worldwide for HPC AI clusters. So while keeping that layer as it is, what has happened is the Ethernet encapsulation layer, which is called as the RoCE V1 and then the RoCE V2, which came with management and IP. That slide actually went inside the upper layer, below the programming layer. So how that helped is that because the APIs, which was exposed to a software or an application to use the InfiniBand, did not change. So what happened is just the Ethernet part, instead of InfiniBand, we came with Ethernet, or we came with Ethernet with layer 3. And the features RoCE had was to make sure not just that the API layer was same, at the same time, in terms of latency, in terms of bandwidth, you had other technologies supporting Ethernet, like what Alan was mentioning about the PFC, ETS, QCN, so that Ethernet could do the job, which is similar to what InfiniBand was doing, right? But that's what is in use right now, and that is fundamentally used very much, other than the InfiniBand world, by all open networking systems. And that is changing to a newer technology we will talk about a little bit later, called as Ultra Ethernet. But then if we go to the next slide, this is again a little walk down history of InfiniBand versus RoCE. So InfiniBand was always a proprietary technology. It was not a standard from ITU, IEEE, or IETF. In between, a technology called as iWARP came in, which wasn't really successful. The reason was because it was not really used by the industry. At the same time, the latency was not up to the mark, and most of for commercial reasons, it wasn't really successful. On the extreme right-hand side is RoCE V2, which was actually built over InfiniBand. And in fact, RoCE V2 is being supported by the same consortium which has been running InfiniBand. So what that gives us is an option with, for example, with Edgecore and OcNOS, is to use RoCE V2 as a transport medium on the layer 2 side for achieving the same result. So we have much more details, but in interest of time, I will tell the most important thing here. One of the problems with RoCE V2, if you come down, what's written in blue in color is it requires a retransmission in case there's a single failure. So it does transmission in batches, and in case there's a single failure, it basically resends the entire previous batch, and that's kind of non-productive, right? So what it requires in that sense is that you need to have all the packets to be sent in order. And it basically needs a lossless fabric at the back end, right? So this is still kind of a problem with RoCE V2. The other little bit of a problem with RoCE V2 is it uses PFC and ETS and QCN as the background lossless technologies, which are kind of a little difficult to configure from a user's perspective. So if we go to the next slide. So what's coming up in the future is something called as UEC. So UEC essentially has basically three fundamental building blocks. So what it has done is it has seen where is the use case for Ethernet, right? So the Ethernet use case right now is in an AI cluster with just a leaf spine with a single hop. So what they have done fundamentally is remove a lot of the overheads which Ethernet had and made it much more simpler. So for example, there's something called as the AI fabric header, which is basically reduces the entire Ethernet packet into much smaller size. You can reuse the same header for layer 2 or layer 3. Then there are two things, interesting things, which has come, something called a CBFC, which is credit-based flow control. This is a concept which is borrowed from InfiniBand. The idea here is, again, is, the receiver tells you an information a priori that if it has sufficient buffer to accept the packets, right? Rather than you sending him and then responding back and there's a ping pong happening. Then on the link layer, they again have come with the technology where from a point to point, in case there's a FEC failure, then you just communicate between the leaf and spine that, hey, there's a FEC failure, please resend me the packet again, rather than going from a leaf to spine, then spine to the leaf, and then communicating all across. So not going again into details, but this is the future which is upcoming. Next slide, please, Al. So what we talked about is on number one here, right? The UEC target networks, and on what you see is the companies which are working on the UEC body. But UEC is not just being planned only for scale out. The future is to also plan use UEC between GPUs, which for the scale up. But that's not the only thing which is upcoming. Now, interestingly, because the AI data centers consume a lot of energy, there are designs which have been done in terms of LPO, in terms of CPO, which essentially cut down the power consumption with more than 40 to 50%, right? And how they fundamentally do is taking the example of CPO, is basically it takes the entire DSP into the main MAC architecture, into the main MAC die fabric. So you don't have a separate DSP which is doing the electrical to fiber and the fiber to electrical conversion. It all sits in a single package that reduces the overall energy consumption. Similarly, something called as LPO. So since you have a leaf to spine, a single hop connection, you don't need a very expensive DSP, which is doing all the error corrections. You just send a packet from leaf to spine, and that again reduces about 40% of the power consumption. And similarly, on the DAC cables have become a little smarter now. They have added a small amplifier, so that helps in becoming a DAC cable a little lengthier, but at the same time reducing the overall power consumption. So these are things upcoming in the future, and both from Edgecore and from IPI OcNOS perspective, we'll be supporting them. Next slide, please.
Oh, thank you, Sujay. So we have come to the end of the presentation. I just want to spend maybe a few more seconds to highlight the benefits of the joint solution. So the IPI OcNOS and Edgecore Ethernet-based open disaggregated networking solution enables customers to leverage ubiquitous Ethernet infrastructure today, while we provide you a clear path to Ultra Ethernet transport in the future. Our core cost effectiveness allows the customers to achieve more with less, while we provide the freedom to choose from a wide and rapidly evolving ecosystem of compatible AI switches and optics with global support. So Ultra Ethernet Consortium specifications, IEEE, IETF, all these are the open standards we adhere to. And that way we can ensure a seamless integration and interoperability with the heterogeneous components from multiple vendors. This will thereby maximize the benefits of disaggregated networking. So that concludes the webinar. And Sujay, maybe you want to take a lead on the Q&A because I'm hosting the presentation. I cannot see the Q&A section.
We open to any Q&A, and please post any questions over here, and we'll be happy to respond. Okay. All right. So the 100 gig switches, the first question is, how about the 100 gig switches? Do they also support lossless features? So the 100 gig switches do not in general support the low-end switches do not support the lossless features in terms of the complete DCBX stack. It's generally supported in the 400 gig to 800 gig category.
I think Trident 3 family also supports PFC and ECM.
Okay.
Yeah. So yeah, so the lossless feature is supported. The full suite of ECM, PFC, ETS, all these things are supported on Trident 3 switches as well for the storage fabric.
So the next question is, why did you choose AMD and Gaudi, and how do they compare? Are they as capable as NVIDIA? So AMD and Gaudi essentially are the two only possible best choices when it comes to other than NVIDIA. So at this point of time, we have AMD and Gaudi as our partners. And when it compares to NVIDIA, it does. So typically it compares to the NVIDIA H100 series. And the different AMD platforms like the AMD MI325, 300, and the Gaudi 2 and Gaudi 3 compare at different levels when it comes to H100 comparison. So as an example, AMD scores fairly well when compared to an H100 when you want to run a very large LLM on it because the HBM memory on the AMD is quite high. So they have capabilities in different areas. And in terms of operational expense also, in terms of a CapEx expense also, the AMDs are much cheaper than an NVIDIA solution. So that's one more reason why we have chosen the AMDs and Gaudis. The third question is, when do you think for AI life cycle will reach to data center state? So typically from our experience, this might take, maybe a 9-month or a 10-month or a year period to enter a data center stage. But I'll let Alan, if you have any comments on this.
Sorry, repeat the question again.
The question was, when do you think for AI life cycle industry will reach to the data center stage?
I don't quite get that question.
So the question was because the company start initially, the deployment in the AI cloud, and then eventually
that. Okay.
yeah.
Yeah, I think it's
Mm.
already happening right now. As shown in one of the slides, we are working with customers across many different verticals. So the customers have already realized some of them started their journey on AI very early on, and they have already tested how expensive that is to run everything out of the cloud. And they are starting to move the data center, the AI operation to their own on-prem data center. So that is actually happening right now.
The next question is slide 15, no GLB, global load balancing. Is it in plan?
That is in plan, yes. Glad that you have noticed that and caught that. And yes, that's coming on our roadmap.
Okay. The next question is, do packets from AI Fabric work? Do packets from AI Fabric, when work with the storage fabric, also utilize RDMA? So yes, from the AI Fabric, when you communicate to the storage fabric, then it does use RDMA. And that was the first fundamental use of InfiniBand, where the servers used to use IB for connecting to which IB essentially, which does InfiniBand, which does RDMA to the storage. So yes, that is true. So we have technologies called as like NVMe over Fabric, or internally it runs RoCE V2.
Yeah. So storage, because it came from a different origin, right? So for AI Fabric, it is purposely dealing with RoCE V2, but storage has been around for so long, and not all file systems are RDMA based, like NFS and many others are not, and they are TCP based. But increasingly, there's a trend to migrate or you adopt the newer storage file system that's RDMA based.
I think the next question is, in your current deployments, do you usually work to interconnect NVIDIA, AMD, and other GPUs? Alan, any thoughts from you?
Let's repeat the question again, please.
The question is, in your current deployments, do you usually work to interconnect NVIDIA, AMD, or other GPUs together? So do we have a heterogeneous GPU system?
We have not encountered that. Typically, one vendor will win the bid, and maybe as time goes on, the newer incremental addition based on different vendor GPU system, we will run into the situation like what this question is asking about.
Correct.
And stay in touch, and we'll share what our experiences if we have a situation like that.
Yeah. So from Edgecore, we have seen situations where the companies start with NVIDIA because that's the market leader. And then eventually when they want to expand, then because now with using RoCE V2 or using the general open networking technologies, you can also switch to an AMD. So we have a customer who's kind of using NVIDIA H100, and eventually they plan to add on AMD GPUs to it from Edgecore. So yes, that's a reality. The next question, Alan, for you maybe is how is DLB managed?
DLB is just like the other networking features. You can, for example, configure it through CLI command. And so there are different modes you can select. This like packet per packet spray mode. There's a random mode where a flow maybe randomly moved or shifted to another link, and there's the floated mode, and this what is, I forgot that name, R the rebalancing mode for the long lead flow. So yeah, so that's you can use CLI command to configure it, enable it, or disable it.
I think the next question is about, do you have any metric on latency, Mellanox versus OcNOS switches? So yeah, so in general, the latency when it comes to Mellanox InfiniBand is slightly better than when you want to use it with RoCE V2, right? But in terms of performance, when it comes to a AI fabric, as you increase the number of loads, it scales linearly. And we have one slide towards the last slide, Victor, if you want to just put it here, slide number 33, which shows a small graph as to how the InfiniBand compares with Ethernet RoCE V2. Yeah. So you can see here essentially, the one which is in black color is RoCE V2, and the blue is Ethernet. So you can see the RoCE V2 is also improving in terms of performance, right? So, and the and it's kind of matching with InfiniBand. So InfiniBand is orange in color, so it kind of matches. So you can't see the orange color because it's overwritten with the black one on the left-hand side. But in terms of as you increase the number of message sizes, the latency increases essentially linear, right? But if you talk a point-to-point latency, then definitely the InfiniBand is better at this point of time. The next question is about, do you have on-site support in Poland and Balkans? So yes, from Edgecore perspective, we do have, and when we work along with IPI, from OcNOS, and OcNOS also has support in Poland and in Balkans. And Alan, if you want to add something to that.
Yeah, we have EMEA sales and the tech support team. So yeah, it is supported in Poland for sure.
The next question is, what option Edgecore has for NOS other than IPI? So both OcNOS as well as IPI as well as Edgecore work in a disaggregated mechanism. So we work with other NOSes as well, but our preferred solution right now for a data center, for AI data center, is OcNOS. So it is well tested and integrated, because one of the things customers always want to have is make sure that they have a good support system, right? So in that sense, we have a good integration, well-tested solution with OcNOS. The next question is, so we can't use a Trident 3 family for smaller GPU clusters, only Tomahawk 5 recommended. So Trident 3 can be used, but the essential problem with the Trident 3 family is the latency is fundamentally high, right? So you do not want to use it even for a GPU cluster, because your GPUs may be sitting idle and waiting for data. So a Tomahawk class of a switch is always recommended for a GPU cluster. And Alan, you want to add anything on that?
In theory, you can use Trident 3, Trident 4 for AI fabric as well. But from density and from latency and from feature perspective, Tomahawk 5 is far more advanced. So there are some features like GOB, and that's only available, and also features like link failure mitigation at the link failover at the hardware level. That's only available on Tomahawk 5. So those may become critical in certain situations, and the only Tomahawk 5 can support those. So Tomahawk 5 is more preferred than others. And it's like design, it's in fact designed more purposely for AI fabric usage.
Okay. The next question, Alan, is for, let me see, what was the question? For the backend network, you use layer 3 BGP. You don't see a need for using an overlay like VXLAN.
We do, and it is a feature coming up on the roadmap. So right now, we are supporting layer 3 GPU, but in the future, in fact, the next release and on, we will have the VXLAN support on Tomahawk 5, and then you can then use layer 2 mode on GPU, and you can apply overlay for the segmentation of different layer 2 groups.
The next question, Alan, is what is the GLB timeline?
GLB timeline is as early as next release, and if not, then the very next one after the next release. So right now we are in 6.6.1 OcNOS wise, version wise, and the next one is 7.0. So GLB is more likely to be in 7.1 release.
Okay. So the next one is, it was not so clear what is UEC and what is it used for in AI fabric. So UEC essentially is an optimization, as you know, we can think it as a brief way like this. It is an optimization over RoCE v2. Because RoCE v2, while is solving the problems what Ethernet has for an AI fabric, the industry wanted to make it much more smarter by reducing the packet headers, by making the point-to-point communication. Essentially, what's happening is people are seeing that the Ethernet piece in AI fabric is only used for a very small segment, just from leaf to spine to leaf. And are there things which they can optimize on the regular Ethernet flow so that it becomes much more faster, right? So those changes essentially have come as a part of UEC consortiums, right? So that's what will be upcoming as a new technology after the RoCE v2. In terms of the next question is related. It says UEC requires hardware support by switch chip, and whether the Tomahawk 5 has a hardware support for UEC. So generally, the RoCE v2 or the UEC technology, which is upcoming, it will be supported by the NIC card, right? So the NIC card, which is sitting on the server, will be supporting UEC, and that will be finally going to the Tomahawk 5. The Tomahawk 5 currently doesn't support UEC. So the newer generations of Tomahawk, which is upcoming in the future, will be having UEC support. The Tomahawk at this point of time, 5 supports RoCE v2 fundamentally, which is currently that's the current support at this point of time. Yeah.
Okay, so I think we have gone way over time. So thank you all for attending the webinar. We're very happy to have you join us. And any further questions, we'll try to get back to you offline. And again, thank you all for attending the webinar. Thank you.
Thank you. Thank you very much.